Every atom in your body was once part of a star that lived and died long ago. That's not poetry, it's science. The stars above aren't just beautiful, they're the reason we exist. We are literally made of star stuff. Ancient civilizations worshipped them. Today, we know stars are born, they burn, and they die in explosions so powerful they reshape galaxies. So when you look up tonight, ask yourself, what are you really seeing? A light show, or the history of everything? Let's uncover the life and death of the stars and why their story is also ours. The birth of a star. Stars are born in the cold, dark expanses of space within massive clouds of gas and dust known as nebulae. Imagine these nebulae as vast cosmic nurseries where the ingredients for new stars are scattered across the universe. These clouds contain the raw materials, hydrogen, helium, and dust particles, that, when compressed under the immense force of gravity, can give birth to something incredible. Gravity is the star's first catalyst. It slowly pulls the gas and dust together, causing the particles to collide and condense, making the cloud denser and hotter. This process takes thousands to millions of years, depending on the size of the nebula. As the gas and dust compress, a new hot and dense core forms at the center called a protostar, but it's not quite a star yet. The protostar is still in the process of gathering mass and energy. The temperature and pressure inside this core continue to rise, and once they hit around 15 million degrees Celsius, something incredible happens. Nuclear fusion ignites. This is the moment when a star is truly born. Hydrogen atoms in the protostar's core start to fuse into helium, releasing vast amounts of energy. This fusion creates light and heat, causing the star to shine brightly. And just like that, a new star is lighting up the cosmos. The process continues, and as the star stabilizes, it enters the main sequence phase, which can last for billions of years. Stars may begin from the most ordinary of elements, but through the forces of gravity, pressure, and time, they evolve into shining beacons in the night sky, marking the birth of something far greater than just light. It's the beginning of a stellar life cycle that will span millions, sometimes billions of years. Main sequence. After a star is born and nuclear fusion takes hold, it enters what we call the main sequence phase. This is the star's stable period, where it spends the majority of its life. Think of it as the star's middle-aged phase, where everything is calm, stable, and most importantly, shining. The star is constantly fusing hydrogen atoms into helium in its core, a process that releases an incredible amount of energy. This energy is what powers the star and gives it its brilliant light. For a star like our Sun, the main sequence lasts for about 10 billion years. That's right, a star is in this phase for a very long time. During this phase, the star has reached a perfect balance. On one side, the energy produced by nuclear fusion creates outward pressure, which tries to expand the star. On the other hand, gravity pulls inward, trying to collapse the star. These two forces, gravity and fusion, counterbalance each other perfectly, keeping the star stable and glowing. For most stars, this is the longest period of their lives. They shine steadily, providing light and heat to their surrounding planets, and if they're lucky enough, they might even give rise to planets with life, like Earth. The main sequence is an incredibly important phase in the life of a star. It's during this time that stars reach their full luminosity, and for us on Earth, it's what allows the stars in the night sky to shine brightly. But just like every good thing, the main sequence phase must eventually end. But before we dive into what happens when the star runs out of fuel, let's just take a moment to appreciate this balance that makes stars like our Sun such essential players in the cosmic drama. This phase represents the peak of a star's vitality, and without it, the rest of the stellar journey wouldn't even be possible. Red giant phase. As a star like our Sun enters the later stages of its life, its hydrogen fuel in the core begins to run low. But don't think that means the end is near. This is just the beginning of one of the most dramatic changes a star will undergo. When the hydrogen runs out, the core starts to contract under gravity's pressure, and in response, the outer layers of the star begin to expand, cool, and take on a reddish hue. Welcome to the red giant phase, where the star grows into a colossal, glowing sphere. At this point, the star's core is much hotter than before, which allows the fusion of heavier elements like helium. As helium atoms fuse together, they form carbon and oxygen, and the fusion process generates even more energy. This energy causes the outer layers of the star to expand massively. In fact, a red giant can grow to be hundreds of times the size it was during its main sequence phase. If our Sun were to go through this stage, it would expand so much that it could engulf Mercury, Venus, and even Earth. Imagine our planet, once teeming with life, now being swallowed by a massive red-hot ball of gas. But even as the star swells in size, things are beginning to change beneath the surface. The increased temperature causes the outer layers to become unstable, leading to massive stellar winds that blow away the star's outer material. In some cases, these winds can carry away up to a third of the star's mass. As the star grows, it starts to shed its outer envelope, leaving behind a dense core. This core will eventually become what's known as a white dwarf, the next phase in the star's journey. While this red giant phase might seem chaotic, it's actually one of the most fascinating stages in a star's life. The transformation from a stable, burning furnace into a massive, unstable behemoth is an awe-inspiring sight. And it's during this time that some stars make their most significant contributions to the universe, creating the heavier elements needed for future star systems and planets. Supernova explosion. For stars that are much more massive than our Sun, the red giant phase is just the beginning of a fiery and explosive end. These stars, once they have exhausted their core hydrogen, undergo a more dramatic and intense series of events that lead to the birth of one of the most magnificent phenomena in the universe, the supernova. But how does this happen? It all starts when the core of a massive star starts fusing heavier elements like carbon, neon, and oxygen into even heavier elements like iron. However, when the core finally forms iron, something changes. Unlike lighter elements, iron cannot undergo fusion to release energy. This creates a major problem for the star. Without the energy from fusion to counteract gravity, the core begins to collapse. The pressure from this collapse causes the outer layers of the star to implode inward at incredible speeds. As the outer layers crash into the dense core, they are thrown outward in a cataclysmic explosion. This is a supernova, a violent, explosive event that releases more energy in a single burst than our Sun will release throughout its entire lifetime. The explosion is so powerful that it can briefly outshine an entire galaxy. During this brief period, the supernova becomes the brightest object in the sky, visible across vast distances. These explosions scatter the star's outer layers into space, enriching the interstellar medium with heavy elements like gold, uranium, and iron. Elements that are crucial for the formation of planets, life, and everything we see around us. Supernovae are essentially the universe's recycling process, creating new building blocks for future stars and planetary systems. But not every star dies the same way. While smaller stars will collapse into white dwarfs, the most massive ones undergo an even more fascinating fate: a neutron star, or, if the mass is great enough, a black hole. But before we delve into these stellar remnants, let's pause and appreciate the sheer cosmic power of a supernova. It's a spectacular end to a star's life and a beautiful beginning for the next generation of stars and galaxies. Stellar remnants. When a massive star explodes in a supernova, it doesn't just disappear into nothingness. What's left behind is a dense, compact remnant that is often more fascinating than the explosion itself. The fate of this remnant depends entirely on the mass of the star's core. There are two possible outcomes for the surviving core: a neutron star, or, if the core is heavy enough, a black hole. Neutron star. For stars with a core mass between roughly 1.4 and 3 times that of the Sun, the core doesn't collapse into a black hole. Instead, it becomes a neutron star, a celestial body so dense that its atoms essentially collapse into neutrons. A neutron star is incredibly small, with a radius of only about 10 kilometers, yet it packs more mass than our Sun. This density means that the star's gravitational field is extreme, and neutron stars are known to emit intense magnetic fields and fast-spinning beams of radiation, which we detect as pulsars. These pulsars can spin up to several hundred times per second, creating a cosmic lighthouse effect. Imagine the power of a star compressed into such a tiny, dense object. For stars with a core mass greater than about 3 solar masses, no amount of pressure can prevent the collapse. The core continues to shrink, becoming so compact that it forms a singularity, an infinitely small point with immense density. This process creates a black hole, a region of space where gravity is so strong that not even light can escape. A black hole doesn't suck everything around it like in the movies, but its gravitational pull is so strong that anything that ventures too close gets pulled in, never to escape. Black holes are mysterious and elusive, but they play a crucial role in shaping galaxies, as most large galaxies have a supermassive black hole at their center. These objects are both fascinating and terrifying, and we can only begin to imagine the mysteries they hold in the depths of their gravity wells. White dwarfs. While the fate of massive stars is marked by dramatic explosions and mysterious remnants, the path of smaller stars, those with less than 8 times the mass of our Sun, is equally fascinating but less violent. Instead of blowing up in a supernova, these stars end their lives as white dwarfs. For stars like our Sun, the transformation into a white dwarf is a quieter, more gradual process, but no less important in the cosmic cycle. When a star like our Sun runs out of hydrogen fuel in its core, it begins to shed its outer layers, releasing a glowing shell of gas and dust known as a planetary nebula. What's left behind is the core of the star, which becomes the white dwarf. A white dwarf is a small, dense object about the size of Earth, but with a mass comparable to that of the Sun. This incredibly dense remnant is made primarily of carbon and oxygen, supported against further collapse by electron degeneracy pressure, a quantum mechanical force that arises from the Pauli exclusion principle. In simple terms, this pressure prevents the electrons in the white dwarf from being squished together. Over time, white dwarfs slowly cool and fade, becoming dimmer and dimmer over billions of years. Eventually they will no longer emit any light or heat, leaving behind a cold, dark relic of the once glowing star. These white dwarfs are not completely lifeless though. In fact, the elements they contain are some of the building blocks for new stars, planets, and even life. The cosmic recycling process continues as the white dwarf's remnants, its carbon and oxygen, might eventually become part of a future generation of stars or planets. Even in death, the star has a profound impact on the universe, passing on the elements needed for new life to take shape. Stars with lower mass end their lives not with a bang, but with a whisper, a slow, silent fade into the cosmic background. But even in their quieter demise, they play a vital role in the ongoing creation of the universe. The cosmic recycling. The death of a star, whether through a supernova explosion, the slow fading of a white dwarf, or the quiet collapse of a neutron star, is not the end of the story. In fact, it's only the beginning of a new chapter in the universe's vast and ongoing cycle of creation and destruction. The elements that were once forged in the heart of a star, hydrogen, helium, carbon, oxygen, iron, and more, are scattered throughout space, enriching the interstellar medium and becoming the building blocks for the next generation of stars, planets, and even life. When a massive star dies in a supernova, the explosion blasts these elements into space at incredibly high speeds, often faster than the speed of light. This cosmic spray of material can travel across vast distances, carrying with it the very elements that are essential for the formation of new stars and planets. For example, our own solar system was likely formed from the remnants of earlier supernovae. The heavy elements that make up the Earth, including the iron in our cores and the oxygen in our atmosphere, were born from the death of ancient stars. Without these stellar deaths, life as we know it would not exist. But it's not just supernovae that contribute to this cosmic recycling process. White dwarfs, the remnants of medium-sized stars, also play a role in this cosmic game of life and death. Over time, as white dwarfs slowly cool and fade, they might still release their residual elements into the surrounding space. These elements could be incorporated into new star-forming nebulae, further fueling the creation of new stars and planets. Moreover, neutron stars and black holes, while seemingly the ultimate end for a star, are not entirely disconnected from the cycle of stellar creation. For example, neutron stars can emit strong bursts of radiation known as gamma-ray bursts, one of the most powerful phenomena in the universe. These bursts of energy can trigger the formation of new stars in distant regions, essentially reigniting parts of the galaxy into new life. Even black holes, with their immense gravitational pull, can influence the formation of new stars by pulling in nearby gas and dust, providing the necessary material for star formation in a process known as accretion. Thus, the death of a star is not a solitary event, it is an essential part of a greater cosmic cycle. Each time a star dies, it releases the ingredients for new beginnings, new stars, new planets, and potentially even new life. The universe, it seems, is forever recycling itself, and each stellar death is a crucial step in this ongoing process of creation. The birth and death of stars are, in a sense, two sides of the same coin, forever linked in the vast, ever-changing tapestry of the cosmos. Thanks for joining me on this incredible journey through the life cycle of stars. From their dramatic births in swirling clouds of gas to their spectacular deaths that seed the universe with new elements, stars truly shape everything around us. The next time you look up at the night sky, you'll see more than just points of light. You'll see stories of creation, destruction, and cosmic rebirth. Stay curious, keep looking up, and keep wondering about the vast universe we call home. And if you love discovering the secret of the universe, don't forget to like, subscribe, and hit the bell icon for more adventures. In 1610, Galileo saw Saturn, but he didn't understand it. His telescope showed strange ears, not knowing they were icy rings that would puzzle humanity for centuries. Today we know those rings are vast, delicate, and possibly vanishing before our eyes, a cosmic masterpiece, fading in silence. Scientists think a lost moon or a celestial collision may have created them. But we still ask, why Saturn? Why not the others? If you stood beneath those radiant bands, would you feel awe or sorrow for what's slipping away? Let's explore the truth behind Saturn's vanishing crown. The enigmatic beauty of Saturn's rings. If you were standing on the surface of one of Saturn's moons, you'd see something that almost doesn't look real. towering arcs of shimmering ice stretching across the sky like a celestial ribbon. For centuries, this sight has mystified stargazers and astronomers alike. Saturn's rings aren't just decoration, they're clues. Clues to a violent cosmic past, to the invisible forces that shape our universe, and to the kind of beauty that only space can sculpt. But what's wild is that when Galileo Galilei first saw them in 1610, he had no idea what he was looking at. His telescope was primitive, and to him, Saturn looked like it had ears. It wasn't until decades later that scientists realized these weren't ears or wings, but rings. Massive, flat rings made of something far more fragile than rock, ice. Not one single ring but thousands of tightly packed ringlets spanning hundreds of thousands of kilometers. They're wide enough to stretch nearly the distance from Earth to the Moon, but they're razor thin, barely 10 to 30 meters thick in most places. So, why do they exist at all? Why Saturn and not Jupiter or Uranus in the same way? That's where things get fascinating. Let's break it down. What Saturn's rings are really made of. Most people think Saturn's rings are solid, like a giant hula hoop floating in space, but that couldn't be further from the truth. These rings are made of billions, yes, billions of tiny particles, each orbiting Saturn independently. They range from microscopic dust grains to house-sized boulders, and they're mostly composed of water ice, which explains why they reflect sunlight so brilliantly. But here's the twist: they aren't pure ice. Hidden among the icy debris are specks of rocky material and organic compounds. That's right, some of the same carbon-rich molecules that may have played a role in forming life on Earth are found in Saturn's rings. Scientists think the difference in ring color, some being brighter, others darker, might be due to the varying amounts of this dusty contamination. And while they look smooth from afar, the rings are more like a cosmic traffic jam up close. These particles constantly collide, clump together, and break apart again. It's chaos, but organized chaos ruled by gravity. Every motion, every gap between rings is shaped by Saturn's moons tugging on the particles like invisible hands sculpting art. And that chaos may hold the key to how the rings even got there in the first place. How did Saturn's rings actually form? A moon torn apart. That's one of the most widely accepted theories behind the formation of Saturn's rings. Sounds brutal, right? And it was. Scientists believe that long ago, Saturn may have had a large icy moon that drifted too close, within the planet's Roche limit, a point where Saturn's tidal forces became stronger than the moon's own gravity. The result? The moon was literally shredded into pieces. But that's just one version of the story. Another theory is even more chaotic. What if two moons collided at high speed, turning into a spray of debris that spread around Saturn like a slow-motion explosion in space? Over time, gravity helped those icy fragments settle into the thin structured rings we see today. This theory is supported by how flat and disc-like the rings are, just like the aftermath of a spinning cosmic smash-up. Some scientists even think these rings could be the remnants of material that never formed into a moon at all, a frozen ghost moon that failed to become whole billions of years ago. But here's the catch. No matter the theory, one thing remains clear: the rings are a result of destruction. Something had to break, rip, or explode for them to exist. Saturn's beauty is born out of cosmic violence, and that makes it even more incredible. Are Saturn's rings old or surprisingly young? You might assume Saturn's rings have been around forever. After all, the planet itself is over 4.5 billion years old. But what if I told you that the rings might be younger than the dinosaurs? That's right. Some scientists now believe that Saturn's rings may have formed as recently as 100 million years ago, when T-Rex roamed Earth. That's practically yesterday on a cosmic timeline. How could something so massive be so young? It all comes down to their brightness. The rings are incredibly reflective, meaning they haven't been exposed to space dust and debris long enough to darken over billions of years. On the flip side, there's a competing theory that says we've just gotten lucky. Maybe the rings really are ancient, but their icy particles constantly recycle themselves, colliding, breaking down, and reforming, keeping them looking fresh and clean despite their age. Cassini's mission tried to settle the debate, measuring how much ring material is falling into Saturn's atmosphere. The data leaned toward a shorter lifespan, meaning we may be living in a rare moment in time when Saturn is dressed in her finest. Either way, the rings are temporary. Whether they're ancient or newborn, they won't last forever. We're witnessing a fleeting masterpiece, and most of the universe won't even get the chance. What NASA's Cassini mission uncovered about the rings. One spacecraft got closer to Saturn's rings than anything in human history, and it changed everything. NASA's Cassini mission, launched in 1997, didn't just orbit Saturn. It danced through its rings, it flew between them, and what it saw was astonishing. Cassini revealed that the rings aren't uniform at all. They're full of waves, literal ripples caused by gravitational tugs from Saturn's dozens of moons. These waves aren't just beautiful, they act like seismic maps. They help scientists understand Saturn's interior structure, the same way earthquakes help us understand Earth's core. Wild, right? And then there were the propellers, tiny gaps carved by moonlets no bigger than a city block. These baby moons move like little shepherds, pulling and pushing ring particles, leaving trails behind like ships through ice. It's a whole ecosystem of motion. Collisions, orbits, spirals, all governed by gravitational forces we can't see but Cassini could feel. What stunned scientists most was the sheer level of detail. They found sharp edges, sudden gaps, and braided structures like strands of hair woven by the cosmos itself. Saturn's rings aren't just pretty, they're alive with motion. Cassini didn't just observe them, it revealed a complex, dynamic system still evolving before our eyes. Will Saturn's rings eventually disappear? They look eternal, but Saturn's rings are fading. Right now, as you read this, those magnificent ice particles are falling, bit by bit, into the planet they orbit. It's called ring rain, and it's caused by Saturn's magnetic field, pulling charged particles from the rings down into its atmosphere. NASA estimates that each second, tons of ring material is being lost forever. Think about that, a structure hundreds of thousands of kilometers wide, vanishing grain by grain like sand in an hourglass. Scientists now believe the rings could be gone in as little as 100 to 300 million years. In cosmic time, that's a blink. And that means we are alive at one of the rare moments in history when Saturn even has rings this bright and massive. Most other planets don't get this kind of spotlight, we just happen to be born at the perfect time to see it. The rings are like fireworks on a galactic scale, stunning, fleeting, and impossible to ignore. One day future civilizations may only see Saturn as a plain gas giant. No icy crown, no shimmering halo, just a memory left in textbooks and telescopes. And that makes every glance at Saturn now feel a little more sacred. The role of Saturn's moons in shaping the rings. Saturn's moons play an incredibly crucial role in the creation, maintenance, and structure of its rings. These moons act as both sculptors and guardians of the rings, exerting gravitational forces that shape the particles within them. Saturn has over 80 moons, but many of them are especially important for the delicate dance of the planet's rings. Some moons, like Pan and Atlas, are small yet vital to the structure of Saturn's rings. They create gaps, or propellers, within the ring material, where the gravitational pull of the moon pushes particles into a tightly packed structure, while leaving a gap in its wake. These gaps resemble the paths left behind by ships moving through ice, and they help maintain the ring's shape and distribution. The effect is not just visual, but also vital for the dynamic behavior of the ring system. On the other hand, moons like Mimas, Enceladus, and Dione have more indirect roles. They interact with the rings by generating gravitational waves, small fluctuations that ripple through the material, organizing it into neat, concentric bands. These waves influence the ring particles' movement and maintain their organized chaos. Through their gravitational interactions, Saturn's moons help to prevent the particles from scattering away into space, ensuring the rings stay intact over millions of years. Interestingly, the material in Saturn's rings is not static, it's in constant motion, constantly being tugged by the moons. This interaction is a prime example of how moons and rings coexist in a delicate balance, with each influencing the other. Without these moons, the rings would likely lack the fine structure and order they currently display. Rather than a simple floating collection of ice, Saturn's rings are a complex, gravitationally controlled system that relies heavily on the nearby moons to sustain its beauty and form. Thanks for joining me on this incredible journey through Saturn's mysterious rings. From icy debris to shattered moons, the secrets they hold are as vast as space itself. There's still so much we don't know, and that's what makes it thrilling. Every new discovery brings us one step closer to understanding the universe we call home. So, what do you think created Saturn's rings? Drop your thoughts in the comments below. Let's start a cosmic conversation. And if you love discovering the secret of the universe, don't forget to subscribe to Space Facts and hit the bell icon for more adventures. Since the dawn of civilization, humans have stared at the stars, yearning to understand our place in the vast cosmos. Ancient astronomers mapped the heavens with curiosity and awe, while today's scientists have uncovered a stunning truth. The universe isn't just expanding, it's accelerating. Yet the biggest question still looms larger than galaxies themselves. What ultimate destiny awaits the universe? Will it stretch endlessly into an icy dark void, or could it one day collapse in a fiery cosmic finale? Join me as we unravel this breathtaking mystery where science meets the edge of imagination, and the future of everything hangs in the balance. The cosmic question. What if I told you the universe is not just expanding? It might be racing toward a fate so strange and mysterious that it challenges everything we know about time, space, and existence itself. This isn't science fiction or a far-off fantasy. It's a cosmic puzzle that has captivated scientists, philosophers, and curious minds for decades. Will the universe stretch endlessly, growing colder and emptier until nothing remains? Or could it one day reverse course and collapse back in on itself, like a giant cosmic heartbeat pulsing through time? Or perhaps even more unsettling, might it tear itself apart atom by atom, unraveling the very fabric of reality? These mind-boggling possibilities sound like something out of a sci-fi novel, yet they come directly from the most cutting-edge research in astrophysics and cosmology. Today, we're embarking on a journey to explore one of humanity's most profound and thrilling questions. What is the ultimate destiny of our universe? Whether you're someone who loves gazing at the stars or simply want to understand the future of everything around us, this adventure will guide you through astonishing theories, surprising facts, and the mind-bending nature of space itself. So prepare your imagination and curiosity, because the fate of the universe may be far stranger and more fascinating than anything you've ever imagined. The Big Bang and the beginning of expansion. Almost 13.8 billion years ago, the universe had its dramatic beginning, not with a bang as the name suggests, but from an unimaginably hot, dense point smaller than an atom. This moment, known as the Big Bang, set everything in motion. From this tiny speck, space itself began to stretch and expand, creating the cosmos we call home. Early on, the universe grew at an astonishing pace during a phase called cosmic inflation, where it ballooned exponentially in a fraction of a second. This rapid expansion smoothed out the universe, setting the stage for galaxies, stars, and planets to form billions of years later. What's remarkable is that this expansion didn't happen in space. Rather, space itself expanded, carrying everything along like dots on an inflating balloon's surface. Scientists have traced back this expansion through observations like the cosmic microwave background, the faint afterglow of that first moment, which acts as a snapshot of the infant universe. Understanding this explosive origin is key because it explains not only how the universe began, but why it's still growing today. But the real mystery starts with the question: will this expansion ever stop? Is the universe still expanding? For centuries, humans have looked up at the night sky and wondered if the cosmos is static or changing. Then, in the 1920s, a groundbreaking discovery shattered old beliefs. Distant galaxies aren't just sitting still, they're speeding away from us. This phenomenon, called redshift, acts like a cosmic Doppler effect, stretching the light waves and proving that space itself is expanding. But here's the twist: this expansion isn't slowing down. Thanks to powerful tools like the Hubble Space Telescope, scientists found that the universe's growth is actually accelerating. The surprising culprit behind this mysterious force is something we call dark energy, an invisible energy making up about 68% of the universe and pushing galaxies apart faster and faster. Dark energy is baffling because we can't see it or measure it directly, but its effects shape everything from galaxy clusters to the very fate of existence. Understanding how and why the universe keeps stretching reveals not just where we are today but where everything is headed. The cosmos is far from static, it's an ever-evolving masterpiece, driven by forces we are only beginning to grasp. Theories about the universe's ultimate fate. When it comes to the universe's future, scientists have outlined three dramatic possibilities, each with its own cosmic drama. The first is the Big Freeze. Imagine a universe that expands forever, galaxies drifting so far apart that stars burn out, leaving a cold, dark emptiness. Over unimaginable eons, everything fades into silence as heat and energy dissipate. The second scenario, the Big Crunch, paints a very different picture. What if gravity eventually overpowers expansion? The cosmos could reverse course, shrinking everything back into a dense, fiery collapse, like rewinding the universe's own birth. Lastly, there's the most extreme and unsettling idea, the Big Rip. If dark energy grows stronger over time, it could eventually tear apart galaxies, stars, planets, and even atoms, ripping the very fabric of reality apart. Each theory depends heavily on the nature of dark energy and how it behaves over cosmic timescales. The fate of everything we know hangs in the balance between these incredible, mind-bending outcomes. What happens next might rewrite the story of existence itself. The role of dark energy. Among the most profound mysteries of the cosmos lies something both invisible and overwhelmingly powerful: dark energy. This mysterious force doesn't just influence the universe, it dominates it, making up nearly 68% of all cosmic energy. Unlike gravity, which pulls things together, dark energy pushes space itself apart, driving the accelerated expansion of the universe. Scientists first suspected its existence when they noticed galaxies speeding away faster than expected, defying the slowing effects of gravity. But what exactly is dark energy? Is it a constant, unchanging force? Or could it evolve over time, perhaps weakening or intensifying? These questions fuel cutting-edge research and debates in cosmology today. Understanding dark energy is crucial because it determines whether the universe will expand forever, collapse, or rip itself apart. Unlocking its secrets may not only reveal the fate of the universe but also challenge our understanding of physics itself. Dark energy remains one of the biggest enigmas, a ghostly presence shaping everything around us in ways we are just beginning to comprehend. Recent discoveries and changing perspectives. The universe is constantly surprising us, and recent discoveries have started to challenge long-held assumptions about its fate. Some new research hints that dark energy might not be as constant as once thought. Instead, it could be slowly weakening over billions of years, opening the door to a future where cosmic expansion could change course, or slow dramatically. This shift in understanding is shaking up cosmologists, forcing them to reconsider how the universe might evolve. Cutting-edge projects like the Dark Energy Spectroscopic Instrument are mapping millions of galaxies with unprecedented detail to track these subtle changes. These observations could redefine cosmic models and hint at new physics beyond our current theories. It's a reminder that the universe's story is still unfolding, and every discovery brings us closer to answering whether the cosmos will expand forever or take an unexpected turn. The journey to uncover our universe's destiny is ongoing, filled with thrilling discoveries that challenge everything we thought we knew. The uncertain future. The fate of the universe remains one of the most profound mysteries we face, an enigma wrapped in dark energy, cosmic expansion, and time itself. Despite decades of research and incredible technological leaps, scientists still don't have a definitive answer. Will the universe continue expanding forever into an icy, silent void? Or will it someday collapse back, triggering a cosmic reset? Perhaps it will unravel at its seams in a violent big rip no one has yet fully imagined. What makes this question so fascinating is how it pushes the limits of our knowledge and imagination, reminding us that we are explorers in an ever-expanding sea of the unknown. The universe's story is still being written, and every new discovery adds another chapter to this cosmic saga. So as we gaze into the night sky, let's embrace the wonder and uncertainty, because it is precisely this mystery that fuels our quest for understanding. The universe may be infinite, but so is our curiosity, and that might just be the greatest force shaping the future of all things. Thanks for joining this cosmic journey into the fate of the universe. If you enjoyed exploring these mind-blowing mysteries, don't forget to like this video, subscribe to Space Facts, and hit the bell icon so you never miss an adventure beyond the stars. Your support helps us bring more fascinating space stories right to you. Got questions or theories about the universe's future? Drop them in the comments. We love hearing from curious minds like you. Stay curious, keep looking up, and get ready for the next incredible adventure with Space Facts. Did you know that La Niña events can reshape weather patterns across the entire globe, affecting millions of lives in ways you might never expect? From fierce storms to intense droughts, this natural climate phenomenon holds enormous power over our planet's future. Understanding La Niña isn't just about weather forecasts, it's about unlocking the secrets of Earth's climate engine. When La Niña strikes, the world doesn't just change, it transforms. What is La Niña and how does it form? Have you ever noticed how the weather sometimes seems to have a mind of its own? Unexpected storms, unusual droughts, or shifts in temperature that don't quite add up? That's often the Earth's way of reacting to a powerful climate pattern called La Niña. La Niña is essentially the cool sibling of El Niño, both part of a climate phenomenon known as the El Niño Southern Oscillation, or ENSO. It happens when the surface waters in the central and eastern Pacific Ocean become cooler than usual for several months. This cooling is caused by stronger than normal trade winds pushing warm surface water westward, allowing cold water from the deep ocean to rise up near the coast of South America. This shift in ocean temperature doesn't just stay put, it sends ripples through the atmosphere, changing weather patterns across the globe. La Niña events typically last from 9 months to 2 years and can repeat every 2 to 7 years. Because the oceans and atmosphere are so tightly connected, these changes in the Pacific can influence rainfall, temperature, and storm activity thousands of miles away. Understanding La Niña is like unlocking a key to predicting some of the most extreme weather events on Earth. Impact on global weather patterns. La Niña doesn't just mess with the weather locally, it rewires the planet's entire atmospheric system. When the Pacific Ocean cools down during La Niña, it shifts the jet streams. Those fast-moving air currents high in the atmosphere that steer storms and weather systems. This shift can cause some regions to experience colder, wetter winters, while others might face hotter, drier conditions. For example, during a La Niña event, the northern United States and Canada often get colder winters with more snow, while the southern United States tends to be warmer and drier. Across the globe, countries in Southeast Asia and Australia usually see heavier rainfall, sometimes leading to floods, while parts of South America like Peru often experience drought. These changes happen because La Niña alters the balance of heat and moisture in the atmosphere, changing how air moves around the planet. The result? A domino effect of weather changes that can disrupt agriculture, water supplies, and even energy demand. The global reach of La Niña is a reminder that what happens in one part of the world's oceans can have far-reaching consequences for millions of people everywhere. Effects on rainfall and droughts. When La Niña kicks in, it's like the planet's weather gets a major remix. Some places get drenched, while others barely see a drop of rain. This isn't random, it's all about how La Niña shifts moisture around the globe. In regions like Southeast Asia and Northern Australia, La Niña often brings heavy rains and flooding. These downpours can replenish water supplies and boost crops, but also cause serious damage when rivers overflow and landslides occur. Meanwhile, places like the southwestern United States and parts of South America often face the opposite drought. The lack of rain can stress farmers, dry up reservoirs, and increase wildfire risks. This push and pull of wet and dry conditions happens because La Niña changes wind patterns and ocean temperatures, which in turn influence where clouds form and where storms track. The result? Some communities might celebrate a season of abundant rain, while others brace for water shortages. Understanding these patterns helps governments and farmers prepare better, but the unpredictability still keeps everyone on their toes. Influence on hurricanes and tropical storms. La Niña doesn't just affect rain and drought, it also turbocharges hurricane activity, especially in the Atlantic Ocean. During La Niña years, the Atlantic tends to see more hurricanes and tropical storms, sometimes with greater intensity. Why? Because La Niña cools the surface waters of the eastern and central Pacific, which reduces wind shear over the Atlantic. Wind shear is like nature's way of breaking up storms before they get too strong. With less of it, hurricanes can grow bigger and last longer. This means coastal areas in the United States, the Caribbean, and parts of Central America face a higher risk of powerful storms. Meanwhile, the Pacific often experiences fewer hurricanes during La Niña, as the cooler waters and stronger winds suppress storm formation there. This seesaw effect between ocean basins shows just how interconnected Earth's climate system is. For communities in hurricane-prone areas, La Niña years are a time to be extra vigilant, prepare emergency plans, and stay informed because honestly, the stakes are higher when the storms come knocking more often. Impact on agriculture and food security. When La Niña arrives, it's like the Earth's thermostat and watering system get out of sync, and farmers around the world feel the impact firsthand. Crops depend heavily on predictable weather. Too much rain can drown plants, while too little can starve them of water. La Niña's shifts in rainfall and temperature can cause both extremes depending on where you are. For example, in places like Australia and Southeast Asia, heavier rains can boost rice and sugarcane yields, but flooding can also ruin fields and delay planting. Meanwhile, drought-stricken areas like parts of South America and the southern United States might see their corn, soybean, and wheat harvests shrink. These disruptions ripple through the food supply chain, pushing prices up and threatening food security for vulnerable populations. Farmers must adapt quickly, sometimes changing planting schedules or switching crops. La Niña's unpredictable nature means that communities reliant on agriculture often face uncertainty, making it harder to plan for the future. The stakes are high because food isn't just about crops, it's about livelihoods, economies, and survival. Effects on marine life and fisheries. La Niña's chill in the Pacific Ocean doesn't just affect the weather, it sends shockwaves through marine ecosystems too. Cooler surface waters and stronger ocean currents during La Niña change, where nutrients rise from the deep, creating feeding hotspots for fish and other sea life. This can be great news for fisheries in some regions, boosting fish populations and catches. For example, the cold, nutrient-rich waters off the coast of South America often support thriving fisheries during La Niña years, but it's not all positive. The altered ocean conditions can disrupt breeding cycles and migration patterns for many marine species. Some fish may move to cooler waters, forcing fishermen to travel farther or adapt to different species. Coral reefs, sensitive to temperature changes, can also be stressed, affecting the entire marine food web. These shifts impact not only ecosystems, but also the millions of people worldwide who depend on fishing for food and income. La Niña reminds us that the ocean and atmosphere are deeply connected, and changes in one ripple through the other in surprising ways. Long-term climate and environmental consequences. La Niña isn't just a short-term weather event, it's a powerful player in the long game of Earth's climate. When La Niña events happen repeatedly over years or decades, they can leave lasting marks on ecosystems, weather patterns, and even human societies. These cycles influence drought frequency, wildfire risks, and the health of forests and wetlands. For example, extended La Niña periods can dry out some regions, making wildfires more likely and stressing plants and animals that rely on steady rainfall. Meanwhile, other areas might see repeated flooding that reshapes landscapes and disrupts communities. On a larger scale, La Niña interacts with global warming, sometimes masking or amplifying temperature trends. This makes predicting future climate conditions even more challenging. For people, these long-term shifts mean adapting how we manage water, agriculture, and disaster preparedness. Scientists study La Niña closely because understanding its patterns helps us prepare for a future where extreme weather might become the norm. It's a reminder that Earth's climate is a complex system, where ocean and atmosphere dance together, shaping life in ways we're still discovering. Thanks for joining us on Space Facts today. If you found this deep dive into La Niña fascinating, don't forget to hit that subscribe button and ring the bell icon so you never miss an update on the amazing forces shaping our planet and beyond. We'd love to hear your thoughts. Drop a comment below and tell us how La Niña has affected your area or what topic you want us to explore next. Stay curious, and we'll see you in the next video.